Like any other subject, part of branch of mathematics, calculus also should begin with numbers only. I hope all of you are comfortable with real numbers. You know what are real numbers. You may not be knowing the precise definition of a real number. I will not ask for that, because even I am not 100% sure of that exact precise definition of a real number. It's enough if you know what real numbers are. You know, mainly there are two types of real numbers. One is rational number, another is an irrational number. Together they make the collection of class of real numbers. What is a rational number? Rational number is a number expressible in the form a by b or p by q, where both p and q are integers and q not equal to 0. For example, is a rational number. Is a rational number. Is a rational number. Yes. Is a rational number. Is a rational number. Is a rational number. Is a rational number. Yes. Every recurring decimal is a rational number. Irrational numbers are those which are not expressible in the form p by q, where p and q are integers, q not equal to 0. In a way, we teachers are cheating you. When you ask what is a real number, I say it is either rational or irrational. What is a rational number? It is a real number expressible in the form p by q. What is an irrational number? It is a real number not expressible in the form p by q. Nowhere we are making clear any of the three items. Everything depends on the other item. Okay, but we can manage with these things. For example, is an irrational number. Proof you must be knowing. In general, is an irrational number as long as a is not a perfect square. Even -1 is not a perfect square. Is root of -1 irrational? No. A is a positive number which is not a perfect square. Okay. Any more examples of irrational numbers? Okay, cube root of 2 is irrational. In general, cube root of n is irrational as long as n is not a perfect cube. No need to say positive number which is not a perfect cube, even it covers negative numbers. Other than this variety, you know any other kind of irrational numbers? Pi, the most familiar number, is an irrational number. Proof is beyond our level. Except my statement, it is an irrational number. It is not expressible in the form a by b. It is, if represented as a decimal, it will not give you a terminating decimal or a recurring non-terminating decimal. Decimal expansion will be neither recurring nor terminating. It will be non-terminating, non-recurring decimal, so irrational. Any non-terminating, non-recurring decimal is an irrational. For example, is an irrational, is another irrational, is a third irrational. Any number of irrationals you may construct like this. Okay. How many rationals are there? Infinitely many. How many irrationals? Infinitely many. Is there any number which is both rational and irrational? No. Is there any number which is neither rational nor irrational among real numbers? No. Every real number is either rational or irrational. No real number is both rational and irrational. Fine. Consider two rational numbers. Can you find another rational lying between the two numbers? Yes, I can. How many? Infinitely many. Between any two rationals, we can insert infinitely many rational numbers. We can also insert irrational numbers. Between any two rationals, there are infinitely many rationals as well as infinitely many irrationals. Similarly, between any two irrationals, there are infinitely many rationals as well as infinitely many irrationals. For example, this is an irrational. This also is an irrational, neither recurring nor terminating. Can you find one irrational between these two? Mention one irrational lying between these two numbers. Yes. Next digit. Okay. Like this, you can insert as many irrational numbers as you like, as many rational numbers as you like. So we find on the real line, there are infinitely many rational numbers, there are infinitely many irrational numbers. Between any two rationals, there are infinitely many rationals as well as infinitely many irrationals. Between any two irrationals, there are infinitely many rationals, infinitely many irrationals. Starting point not known minus infinity, ending point not known minus infinity. Take any interval of any length, even a very small length, it will have infinitely many real numbers. Of them, infinitely many will be rational, infinitely many will be irrational. All varieties are there. There is some sort of, do you feel there is some sort of congestion on the real line? No. Even though there are infinitely many many real numbers, alternately rational, irrational numbers, they are all in a proper order. They are all standing in a queue, one behind the other. There is no overcrowding. There is no person standing outside the queue. All are in a particular disciplined, standing in a disciplined manner. There is perfect order in the set of all real numbers. One of the most important properties of real numbers is comparability. Give me any two real numbers, I will be able to say either this number is less than that or one of the three. Either this number will be less than that or that number will be less than this, or the two numbers will be equal. One of the three must hold and will always hold. Law of trichotomy it is called. Between any two real numbers, always one of the three relations, one and only one of the three relations always holds. This is a special property of real numbers, not possessed by all number systems, and one of the most useful properties also. This relation not only usable, it also has number of properties. Some of the simple properties are: you can add any number to both sides, you can subtract a number from the two sides, you can multiply the two sides by a positive number. Only positive numbers you must use as multiplier. If you multiply the two sides by a negative number, inequality reverses. If you multiply the two sides by 0, inequality gets replaced by equality. Only by positive reals the two sides can be multiplied, but while adding or subtracting, any kind of number you can use. As a consequence, we will have, if both the numbers involved are positive, you will also have in general for every positive rational n. If both a and b are positive, then a less than b implies a power n less than b power n. If both a and b are negative, then a square will be greater than b square, a cube less than b cube, a power 4 greater than b power 4, a power 5 less than b power 5, so on. And if you are raising the two numbers to a odd power, there will not be any need to be careful. Whatever be the signs of the numbers, whether they are both positive or both negative, each number can be raised to any odd power. For example, if a is less than b, whatever be the signs of the numbers, either both must be positive or both must be negative. Even you can have one positive, one negative, will hold for any positive integer n. Okay? But if you are raising the two sides to a even power, you will have to be careful. You will have to apply the procedure only if both the numbers are positive or both are negative. When both are negative, something different will take place. If both are positive, inequality will continue as it is. Okay. So, what is the meaning of this? X lies outside the interval minus root 3 plus root 3. Either x is greater than root 3 or x is less than minus root 3. Even that is possible. For a number less than minus root 3, square will be greater than root 3. Okay. What does this mean? Either x square lies between root 2 and root 3 or it lies between minus of root 3 and minus of root 2. Okay, maybe positive, maybe negative. When positive, it will be between plus root 2 and plus root 3. When negative, it will be between minus root 3 and minus root 2. Just this much. X lies between minus 2 and plus 2. Lies between minus 2 and plus 2. Within the open interval minus 2 to 2. Now it will be between minus 2 and plus 2 including the endpoints, closed interval minus 2 to 2. Means x lies between, what are the points where these two vanish? This vanishes at minus half, this vanishes at 1 by 3. The product will be negative only when x lies between minus half and 1 by 3. For numbers between these two, product is negative. For numbers outside, the product will be positive. Okay. X lies outside. First address the smaller number, minus 2 and 1. It lies outside minus 2 and 1. Okay. What does this mean? Okay. How did you get an answer for the previous question? I asked what will be the meaning of this inequality. You said x must lie outside minus 2 and minus 1. How did you get that conclusion? Actually, that was obtained considering several cases. the different numbers involved are x plus 1 and x plus 2. This vanishes at minus 1, this vanishes at minus 2. You locate the points minus 2, minus 1 on the real line. These 2 points divide the real line into 3 parts. One part minus infinity to minus 1 and minus 2, another part between, a third part outside. The 3 possibilities are x may be here, x may be here, x may be here. You just examined what happens if x is here. X is less than minus 2 means this will be negative, this will also be negative, the product will be positive. Next you consider this possibility, x is between, then this will be negative, this will be positive, the product will be negative. Next you will consider this possibility and you will find the product positive, and that leads to your conclusion. Same procedure if you are trying to extend. What are the points where the various factors vanish? Let us mark those points on the real line. One of the points is 1, another point is minus 2, minus 3. I am not marking the points according to scale, I am only giving importance to the positions, left side, right side, that part I am taking care of, scale I am not following. Okay, next is plus 4, minus half, where should I mark it?
Plus 5, minus 6.
Okay. Next what I do is, according to my logic, I must consider an arbitrary x in this interval, then find out what happens to that expression. Next must consider an arbitrary point of this, consider determine what happens to that expression, continue like that. But our experience with that we have gained while working these simpler problems suggests us a somewhat shorter approach. Choose a random point belonging to this interval, point according to your convenience, any point to the left of minus 6, say minus 7. At minus 7, this is negative, remember it, negative, product positive, negative, product negative, negative. So numerator is positive now, am I right? Yes. My point is minus 7, negative, 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 everything is negative. So is the inequality satisfied? Yes. That means this is a part of my solution set. If this is a part, this will not be a part, this will be, this will not be. Our experience suggests us this will be, will not be, will not be. So what is the solution set? Minus infinity, starting from minus infinity to minus 6. Is minus 6 included? No, our inequality is strict. Okay, open interval. This is not to be included. Union, again open interval, union, union. This is the solution set for our inequality. Okay. Okay, how do you solve this inequality? We notice that there are some powers in the factors. Some of the powers are odd, some powers are even. We can easily get rid of those even powers. We know one property of real numbers. Take any real number, positive or negative, when you square it, when you raise it to an even power, the number becomes positive, strictly positive. Therefore, this can never be negative. This can never be negative. This can never be negative. And when you have an inequality, you are permitted to multiply the two sides by a positive number. And therefore, you are also equally permitted to divide the two sides by a positive number. Inequality will not be affected by multiplication or division by a positive number. Am I permitted to divide the two sides by x plus 2 whole square? It's a non-negative number, is it not? I said it is non-negative. I didn't say it is positive. Yes, what happens? I can divide, but with the correction I can divide. Yes.
X is not equals to minus 2.
This cancellation permitted only if x is not equal to minus 2. What happens if x is equal to minus 2? Is the inequality satisfied? Yes. This will be 0 and you are permitted to have the expression 0. So remember that minus 2 is a solution obtained by inspection. Minus 2, if minus 2 is discarded, kept outside, our inequality becomes this. Agreed? One solution has been obtained, minus 2. To obtain the remaining solutions, we must solve this. Agreed? Three solutions are obtained by inspection. To obtain the remaining solutions, we need handle only this much. Agreed? Yes. Is there any way to reduce the power? This higher power, yes, I am not comfortable with that. Is there any way to get it reduced? Just divide by x plus 3 whole square, which certainly is a non-negative number. Okay, the power gets reduced to 1. Should I include minus 3? No need, because we are retaining one of the factors. There will be no need to include minus 3 to this list, because minus 3 is covered there. Minus 3 is a solution of this inequality. No need to include it separately here. Okay, this is the inequality you need solved now. Very simple. You know the method, what to do. Just identify the points where the individual factors vanish, locate them on the real line, find out. Let me complete. What are the points? 1, minus 3, minus half, minus 6. Okay, that's all. Sample point. Okay, I will choose a different sample point. I will choose this interval. A sample point belonging to this interval is 0. Okay. At 0, negative, positive, positive, positive. Is the inequality satisfied? Yes. So this is a part of the solution set. Agreed? This cannot be. This cannot be. This has to be. This cannot be. Okay. What are the solutions? Is minus 6 a part of the solution set? No, because the factor x plus 6 is in the denominator. Because it is in the denominator, you are not allowed to assign the value minus 6 to x. Inter will be open at minus 6. What about right hand point minus 3? Can you include it? You can. The factor is in the numerator. Next, this one. What about inclusion of minus half? No, you can't do it. What about inclusion of 1? Yes. Any other thing to be included? No. Then these 3 points. Okay? Huh? Okay, 5 is in the denominator. Sorry. Yes. Agreed? Can any of those points be included in one of the intervals? No. None of the intervals has an end point equal to minus 2 or 4. The set has to be left separately. Okay. Any help? First we will have to get rid of the denominators. Consider this denominator, x square plus x minus 1. It is a quadratic. A quadratic need not always attain the same sign. It may be always positive, may be always negative, may be sometimes positive, sometimes negative. When will a quadratic be always positive? Consider the expression ax square plus bx plus c. I may write this as a into x square plus bx by a plus c by a, may be written as x plus b by 2a whole square. This is called method of completing squares. I am getting ax square, I am getting a into 2 into x into b by 2a is bx. Yes. As third term I am getting a into b square by 4a square, or it is b square by 4a. I must remove that b square by 4a and then include the required constant term c. This is what I am getting. Or this is a into x plus b by 2a whole square minus this being a perfect square has a least value. This cannot go beyond a certain limit. This cannot be less than 0, must be always greater than or equal to 0. Agreed? That suggests the minimum value of this expression is minus of b square minus 4ac by 4a. The least value this expression can attain is minus of b square minus 4ac by 4a. Agreed? Yes. The expression will be always greater than or equal to minus of b square minus 4ac by 4a. If this is positive, then this expression will be always positive. If this expression is negative, this expression may be partly positive, partly negative. Agree? No, I was wrong. My statement needs a correction. Everything that I am mentioning depends on the sign of this a. As long as this a is positive, for this only you said the least value is 0. That does not mean for this product the least value is 0. It depends on a. If a is negative, even though this is greater than or equal to 0, this product will be negative. Is it not? So the least value of the expression may go down. Is it not? Consider the case a positive first. When a is positive, this is greater than 0, greater than or equal to 0. Therefore, least value of the expression will be this. And if this is positive, this will be always positive. If this is negative, this will be partly positive, partly negative. If this is 0, this is always greater than or equal to 0. Agreed. What happens if a is less than 0? Again, everything depends on this. This will be now a number which is less than or equal to 0. Suppose this is a positive number. Our expression is this positive number to be added with a negative number, a number less than or equal to 0. The sum will be less than or equal to this number. This will be the highest value attained by the expression. Agreed? Yes. If this highest value is negative, the expression will be always negative. If this highest value is positive, expression will be partly positive, partly negative. If the expression is 0, this will be always less than or equal to 0. Okay? When you draw the graph will look like when A positive, this is the least value. And when is this value attained by the expression? When will the value of the expression be equal to only this much? When this part is 0. When is this part 0? X equal to minus b by 2a. So for this point, x coordinate will be minus b by 2a, y coordinate is this much, this expression. Let me write it here, that will be more proper. Agreed, I think? Yes. If this point is below the x-axis, our expression will be partly negative, partly positive. For points between this point and this point, our expression will be negative. We have noticed it earlier also. A quadratic is negative if x lies between certain points. A quadratic is positive when x lies outside certain points. In all those examples, I took a positive, x square coefficient positive, that is this case. Okay, the expression will be partly negative, partly positive. If this point lies above the x-axis, if the x-axis position is this, expression will be always positive. If this is the position of the x-axis, the expression will be always greater than or equal to 0. When a is negative, the shape of the parabola will be like this, with x coordinate of this point minus b by 2a and y coordinate as before, same thing, 4ac minus b square divided by 4e. This y coordinate positive means x axis is somewhere here. Expression is partly positive, partly negative. The position of the x axis is here means the expression is always less than or equal to 0. Now the expression is throughout negative. Okay? This information sometimes may help us in solving some numerical examples. We will be making use of these ideas again and again. Now where is my problem? Okay. I wanted to get rid of the denominators of this fraction. The first fraction has a quadratic in the denominator, x square plus x minus 1. What can you say about the sign of this quadratic? Is it always positive, or it is partly positive, partly negative, or it is throughout negative? Because your x square coefficient is positive, it cannot be throughout negative. Either it must be partly positive, partly negative, or must be throughout positive, or throughout greater than or equal 0. What is the case? Yes. Did I make any mistake in calculating this expression? No, I think. In ax square plus bx plus c. Suppose you replace x by minus 2a, minus b by 2a, a into b square by 4a square plus b into minus b by 2a plus c. When simplified, are you going to get that expression? Right, I think. No mistake has been committed. Okay. Yes, what about the sign of this expression? What about the sign of 4a? Positive. What about 4ac minus b square? 4ac minus b square? Negative. That means point is below the x-axis. That means our expression is partly positive, partly negative. We need find when is it positive, when is it negative. Consider two cases. Case 1, when this is positive, we safely multiply the two sides by the expression. Case 2, when the expression is negative, we multiply the two sides but reverse this inequality. Okay, let me simplify my work because I am trying the problem. I want the problem to be simpler. Is this always positive? Yes. I can multiply the two sides. There will be no effect on the inequality. Next job will be to get rid of this denominator. I cannot avoid considering cases. I have to consider two cases. Case 1, x less than 1. Case 2, x greater than 1. If x is less than 1, this will be negative and multiplying will reverse the inequality. In the other case, inequality will be retained. Okay, two possibilities. What will happen? Changed or as it is? As it is. Simplify. Minus 2x plus x minus 1. Simplify further. You know how to finish this. You will just find where this expression vanishes. Find the roots of this, the equation obtained by equating this quadratic to 0. You will get two roots. You want the expression to be negative, x square coefficient is positive, x must lie between the roots. What are the roots of this? Let me finish the job. Is this a factorizable expression? What is b square minus 4ac? Is it a perfect square? No. So it is not factorizable. Okay, what are the roots? Minus b plus or minus root of b square minus 4ac 12. Is it? Yes. Divided by 2a 2. These are the roots. Or when simplified, these are the roots. Agreed? X must lie between these roots. The inequality is strict, so x must lie strictly between the roots. But all these numbers, do they form part of the solution set? No. This part we got applying the condition x greater than 1. So among the numbers satisfying this, retain only those numbers which satisfy this. Which numbers satisfying x greater than 1 also satisfy this? What is the position of the number x equal to 1 with reference to these two numbers? Will it be a number outside this interval or will be a number inside the interval? Inside. So 1 is somewhere here, and the condition applies only for x greater than 1, means the obtained part of the solution set is yes 1 agreed. This is one part of the solution set, that part which satisfies the condition x less than 1. What happens if x is less than 1? This inequality will be reversed. This will be opposite. This will be opposite. The quadratic with x square coefficient positive will be positive when x lies outside the roots. What are the roots? Minus 1 minus root 3 and minus 1 plus root 3. X must lie outside the roots, then only this inequality will be satisfied. Agreed? But among these numbers, which numbers satisfy the condition x less than 1? Where is 1? Somewhere here. I want x to be less than 1. Means minus infinity to okay. Will be the solution set for my inequality. Agreed? leave the numbers aside. We will get back into real numbers a little later. Before that, consider one set. You know, all of you know what is meant by a set. Any well-defined collection of objects is called a set. You know what is meant by well-defined also. You have enough examples of collections of elements which are called sets, which are not called sets. Consider a particular set. One example I will take. This is collection of members of a family, head of the family. I assume the head is a male. This is his partner, wife. This is the father, father of H, mother, mother-in-law, son, only one son he has. 2 daughters. She is daughter of D1, small d1. Okay. Is a family. Within a family, between members of a family, different kinds of relations exist. In this family also, we have a number of relations. Is a son of, is a relation. Is the father of, a relation. Is the mother of, relation. Is granddaughter of, relation. Is grandson of, relation. So many relations are there. Consider any one example. Say, is a son of. Spelling. What are the relationships that exist? Yes? In this small relationship itself, I am finding a repeated mention of these words. Normally in mathematics, we are fond of symbols. Whenever repeated occurrence arises, we try to abbreviate that expression or that sentence that is repeatedly occurring. Let me here also, instead of using these marks, let me symbolize the relationship. I will use the symbol. This is a son of. I will use this symbol to denote the relationship. So my statements take a simpler form. H is son of F, H is son of M, so on. Even this, if you find inconvenient to use, still further abbreviation you can try. Why should you write each time this symbol again and again and again? Let us use some other notation. Instead of writing this entire statement, I will simply write an ordered pair. And whenever I use this ordered pair, I will mean H is a relative of F under the given assigned relationship. So the ordered pairs I get will be HF, HM, SH, SMP. SMP. Do you have many more any? What about S? No, just P. Is it not? Yes. Is there any more relationship of this kind? No. This completes the description of that relationship that I am considering. So I can say my relationship is completely described by this set of ordered pairs. I find every relationship describable by a set of ordered pairs. Whenever there is a set A and there is a relationship defined on A, I can have that relationship described as a subset of A cross A. Whenever there are two sets A and B, there is a relation between members of A and members of B. That relationship completely can be described by a subset of A cross B. Every relation between members of A and members of B is obtainable as a subset of A cross B. Every relation that exists between members of a set A is obtainable as a subset of A cross A. So, I define a subset of A cross A to be a relation on A. Any subset of A cross B defines a relation from A to B. Certain relationships may have verbal explanations like this. Many relations that I get in my process may not have verbal explanations. For example, in this case, say HD1 MLS also is a relation from A to A, is a subset of A cross A. But I don't think I have a verbal explanation for this relationship. But theoretically, this also is a relationship. According to me, whenever there are two sets A and B, every subset of A cross B defines a relation from A to B. Every subset of A cross A defines a relation from A to E. Okay. How many relations you can define on a set A? Suppose set A contains 5 elements. How many relations you can define on set A? Okay. According to our definition, relation on A is a subset of A cross A. My set A has 5 elements. First I will write A cross A. How many elements will this have? 25. How many subsets will this have? How many digit number it is? You said 32. What is the difference between the actual answer and your answer? Almost infinite. More about relations not needed from our point of view, I think. There are two ways of handling relations: algebraic method, calculus method. Algebraically, you can speak of some properties. A relation can be reflexive, relation can be symmetric, relation can be transitive, relation can be an equivalence relation. For example, symmetry means if A is a relative of B, then B is a relative of A. Reflexivity means A is a relative of A for every A. Transitivity means if A is a relative of B, B is a relative of C, then A is a relative of C, so on. One example, relation is a brother of. Is it transitive? First, is it symmetric? Suppose A is a brother of B. Should B be a brother of A? These people are saying no. B may be a sister of A. Okay, not symmetric. What about transitivity? Suppose A is a brother of B, B is a brother of C. Should A be a brother of C? Now question of sister does not arise. A is a brother of B, B is a brother of C. Should A be a brother of C? No. Relation is neither reflexive nor symmetric nor transitive. Why? Think of. Think of. Okay, that treatment we do not require. Ours is calculus point of view. Any subset, if A and B are two sets, any subset of A cross B, you said, is a relation from A to B. Arbitrary relations you can form on A cross from A to B, we get a large number of relations. Even for a small set with A with 5 elements, we found 2 to the power 25 relations are possible from A to B. All these relations cannot be interesting relations for us. From calculus point of view, this simple relation is not an interesting relation, is not interesting from our point of view. We impose some conditions on it and we make it a thing with some attractive properties. So we make it a function imposing certain conditions. By definition, any subset of A cross B is a relation. For example, is this a relation from A to B? Yes. What are the members of that relation? Ordered pair 1A, ordered pair 2B, ordered pair 2D, ordered pair 3C. Under this relation, every element of A has a relative. 1 has 1 relative, 2 has 2 relatives, 3 has 1 relative. Element 4 has no relative. Not an interesting relation. Relation becomes more interesting if every element here possesses a relative. Also, one more condition, every element has a single relative in the other set, in the set B. So this is not a function. A function is a function is a relation under which every element of this set has a relative there. Every element has a single unique relative in that other set. Now B has 2 relatives, one relationship I will discard. I will have a single relative for A, single relative for 2, single relative for 3, but still is not a function because 4 has no relative. Let us assign a relative for 4, no problem. I can use C again and again, no problem. This is a function from A to B. Condition to be satisfied, it must be a relation. Under the relation, every element of A must have a relative. Every element of A must have a unique relative. Then only the relation becomes more interesting for us. We will call it a function. We will assign a special name to it. We call it a function. This is a function. Is this also a function? Yes. No. No. Yes. Suppose A has 3 elements, B has 2 elements. How many functions can be defined from A to B?
6.
In order to obtain a function, I have to assign an image for each of the elements here. For A, I must assign an image. For B, I must assign an image. For C also, I must assign an image. For A, in how many ways I can choose an image? I can choose 1 as image or 2 as image. I have 2 choices. Independent of the element chosen as image for A, I have 2 more choices for defining an image for B. I can reuse 1 if 1 has already been used. If not used, I can use 1 or 2, any one of the 2. Again 2 choices. For C, again 2 choices. Okay? Is it 6? How many are possible? M power n or n power m? N power n. This is another way of representing a function or relation. Instead of writing the function or relation as set of ordered pairs, I have used the graphical method. I have defined an image for 1. This is the image for 1, the height. For 2, I have defined an image. For 3, there is an image. For 4, there is an image. For 0, I have not defined an image. For half, I have not defined any image. For any number greater than 4, no image has been defined. For a number between 3 and 4, no image. Is this relation a function? What I have shown in the graph, is this graph of a function? Yes, no problem. Every element that has been chosen by us has a unique image. I am not defining multiple images for any of the elements for which image has been defined. Can this be graph of a function? Yes. No, why? For certain numbers we are getting multiple images. Okay. Condition that a graph may represent a function is every vertical must intersect the graph in at most one point. Either it should not intersect. If it intersects, it must intersect at one point. Should not intersect in more than one point. Okay. Is this also a function? Yes. Even now, is this a function?
Yes.
No problem. Why not? Yes. Yes. These are identical. No need to write this once again. But if it is written, no problem, there is nothing wrong. Okay. Okay. Is a function. I want to name this function. You can name using any symbol you like. Naming is at your you have the freedom. You can choose any symbol of your liking to name a function given, but normally more popular, more frequently used names are letters like F, G, H, or Greek letters like psi, xi. Such symbols are normally made use of. Let me name this function by small letter f. Then I may use certain notations. 1, 2 is an ordered pair belonging to f. I will symbolically write it as f of 1 equal to 2. If the name of the function is g, I will write g of 1 equal to 2. If the name of the function is phi, I will write phi of 1 equal to 2. I also have f of 2 equal to 2, f of 3 equal to 2, f of 4 equal to 7, and f of 5 equal to 0. Also, I may write f inverse of 1. By inverse, I mean the collection of pre-images. For this element, this is called an image. For this element, this is the image. For this element, this is the image. For this element, this is a pre-image. For this element, this is a pre-image. For this element, this is a pre-image. So, when I write f inverse 1, I mean the collection of pre-images of 1. Which are all the elements having image 1? No element has image 1. It is an empty set. There are 3 elements. Remember, this is always written as an element because you are sure for every element there is a single image. No need to describe it as a set. Because you have single image for every element, you can write it as a number, as a single element. But in this case, you are likely to have multiple elements. You have to use the set notation. It will be defined as a set of all pre-images. So, in this case, 3 pre-images. Empty. Even though there is a single pre-image, you describe it as a set only, not without flower brackets. Okay. For this function, the collection of elements having images defined will be called the domain. The collection of all image elements will be called range. So for this set function, the domain is the set 1, 2, 3, 4, 5. The range is the set 2, 7, 0, is a 3 element set. Whenever a function is defined from A to B, A will be the domain of the function, B will be the codomain of the function. In B, every element need not be an image element. Collection of only those image elements taken will form the range. All elements of B together form the codomain, and collection of just image elements will form the range. This will be the domain. Always this will be the domain. Here every element will have a image, but here every element need not have a pre-image. Those elements having pre-images put together form range. All elements put together form the codomain. Okay. So for this set, the domain is 1, 2, 3, 4, 5. Range is 2, 7, 0. Domain is 1, 2, 3, range is 1, 2. Domain is closed. I didn't mention whether this point is a part of the graph or not. If I use this notation, it means point is part of the graph. This means point is not a part of the graph. This means point is not to be included in the graph. This means point is a part of the graph. So domain will be closed at half, open at 2, and range is even 2 is attained by the function, so the range will be closed interval. Okay. Is this also a function? Yes. Domain 1, 2, 3, 4. Range 1, 4, 9, 16. I have described the function which is a set in the tabular form. But a set normally is representable in several ways. One is tabular method. Another popularly used method is the rule method. You can describe sometimes sets by rules also, using rules also. In this example, it is possible. I can describe the set also as set of all xy such that x is equal to y square or y equal to x square. Okay. When such a representation is possible, this is not always possible. Suppose I consider the function it may not be possible to describe it by means of a rule. When it is possible to express a function by means of a rule, what we do is we will have an understanding. This will be a more interesting for us, function for us. We will be repeatedly or more frequently confronting functions of this kind. So we will have an understanding. Instead of writing all these details, we omit certain parts, we omit these things and simply write y equal to x square, x belongs to that set, or f of x equal to x square, x belongs to that set. It's enough if you write like this. You will understand by this what the meaning of the relationship is, what exactly is the function under discussion is, you need not mention all these details. Strictly speaking, a function must be expressed as a set because it is a particular kind of relation, and relation by definition is a set. Strictly speaking, all these things are necessary, but we can have the understanding, we can simply write like this and have a function represented by equations of this kind. We are more interested in functions which are obtainable by formulae like this, and not by functions which are expressed as set of ordered pairs, or by means of Venn diagrams, or by a graph consisting of stray points. Such functions will not have good number of properties, will not be interesting functions for us. In this case, we can expect some more things, some properties, nice properties we can expect of these functions. So we will be interested in functions of this kind, functions which are obtainable in formulae form. Such functions are functions which are of interest, and only such functions we will be dealing with in calculus, in our study of calculus. Okay. This function, actually my function was x square, x belonging to 1, 2, 3, 4. I had explicitly mentioned x is an element of this set. So it is clear from the definition itself that the domain of the function is 1, 2, 3, 4. Range I can calculate. Sometimes only this formula will be given, this will not be mentioned. In the absence of any such instructions, you should accept that the domain of the function is the set of all real numbers x on which you can apply this formula. For which numbers you can compute x square, take the collection of all such numbers, that forms the domain for this function. If any instruction is there, you accept it. You define, you have the domain according to that instruction. In the absence of any instruction, domain will be the set of all x such that x square is meaningful. In this case, the domain will be whole of real numbers, minus infinity to infinity. For any number you can find the square. It is the entire set of real numbers from minus infinity to infinity. Suppose your function is defined by this formula, domain cannot be the entire set of real numbers. Domain will consist of only non-zero reals, or as a union of intervals. Agreeable? Yes. Domain will be all real numbers. Why should you exclude 0? Can you apply the formula at x equal to 0? Yes, I get a negative number, no problem. Is it not possible to apply the formula at every point? Yes. So the domain will be the set of all real numbers, except 3 by 2. Every real number other than 3 by 2. All real numbers greater than or equal to 3 by 2. In order to obtain square root, the number under the radical sign must be greater than or equal to 0. Strictly greater than 1. Okay. This is a quadratic now. A quadratic need not be always positive. Under what conditions a quadratic will be positive? Is this a quadratic with the x square coefficient positive? Yes. When will it be positive? When x lies outside the roots or between the roots? Outside the roots. What are the roots? 1 and 2. Therefore, the domain will be outside. What about inclusion of 1? should not be included. 1 x minus 1 is in denominator. Denominator cannot be 0. Denominator cannot be 0. Agreed? Yes. What kind of quadratic is this? It's a quadratic with the x square coefficient negative. For a quadratic with the x square coefficient negative, when do you get a positive sign? When x lies outside the roots or between the roots? For ax square plus bx plus c with a positive, you get positive sign outside, negative sign between. Now you have a negative, so positive sign between and negative sign outside. Domain will be endpoints to be included or excluded. Agreed? Let me find the range also. Why should I leave the range? Again, why should I take up the same examples for determination of range? This is the domain. Okay. What is the range for this function? To obtain the range, what I do is, yes, any help? Consider the graph of the quadratic x into 1 minus x. The function under the radical sign is negative of x square minus x minus x square, let it be. Draw a graph for this function. The graph for any quadratic is a parabola. For a quadratic with the x square coefficient positive, graph will be a parabola with vertex below. For a quadratic with the x square coefficient negative, graph will be a parabola with vertex above. This is the vertex. This is the vertex. This will be the graph when a positive. This will be the graph when a negative. For this vertex, in any case, whether you consider this or this, the x coordinate is always minus b by 2a. While applying the formula for finding the roots of quadratic, the formula is minus b plus or minus root b square minus 4ac by 2a. That rational part, minus b by 2a, forms the expression for x coordinate of the vertex. Okay. This is a quadratic with x square coefficient negative. So graph will be a parabola with vertex above. Let me draw the x and y axis later. Graph will be like this. For the vertex, the x coordinate will be minus b by 2a. A is minus 1, b is 1. Ax square plus bx plus c. So a is minus 1, b is 1. Minus b by 2a is the x coordinate of the vertex. Half plus half. Okay. When x is half, what will be the value of x minus x square? Half minus 1 by 4. 1 by 4. So what will be the positions of the x and y axis? X coordinate is half. So y axis is on this side. Y coordinate is 1 by 4. X axis is below. Agree? 1 by 4 units below and half units to this side. What will be x coordinate of this point? The point when this vanishes. When is this? 0 and 1. Agreed? 0 means it must pass through the, it must be a point on the y axis. Agreed? Yes. So our parabola partly lies above, partly lies below. I want the function to have the quadratic to have a square root. To have a square root, the expression must be positive. We have already noticed x must be between 0 and 1. So this is the domain of the function. What is the range? For this expression, x into 1 minus x, the values lie between 0 and half. Agree? This is for x into 1 minus x. So for the square root, the values will be between 0 and these are not between 0 and half, I am sorry, it's between 0 and 1 by 4. X into 1 minus x lies between 0 and 1 by 4. The square root will lie between 0 and 1 by 2. Denominator lies between 0 and half, reciprocal lies between or lies outside. The denominator is a number between 0 and half. Denominator can be any number between 0 and half when you apply reciprocal.
0.
Guess. Not 0, not 0. Denominator is some number between 0 and half. Take sample values. For denominator equal to 0, it is infinity. It is plus infinity or minus infinity. Your values are between 0 and half. You are not having negative numbers. You are having only positive numbers close to 0. Therefore, reciprocal will be plus infinity. For half, reciprocal is 2. Take a number in between, 1 by 4. Reciprocal is 4. Is it between or outside? Outside. What about other values? Is it difficult now? Finding reciprocal of numbers between 0 and half. No, must be possible. What is graph of y equal to 1 by x? Rectangular hyperbola. Our denominator is taking values from 0 to half. So values must be between 2 to infinity. Okay, I misplaced, the positions are wrongly noted down. Infinity is smaller, not smaller than 2. Infinity is should have been written on the other side. And we are finding one sample value as 4, a number in between. Therefore, the range will be 2 to infinity, with the 2 to be included or excluded? Included. There was no need to use this. Directly we could have obtained, provided had I written infinity on the other side. Misplacing of the numbers. What is the time now? Should I over? More problems are to be tried under finding domain and range. Actually, from my point of view, this is the one of the most required, one of the areas which is to be given enough importance, or more than a normal level of importance. I give too much importance to domain and range, so I want a variety of problems to be covered under this section. Only afterwards we will proceed further. The real part of calculus is discussing continuity, differentiability, etc. But before that we should have a strong foundation. For that we require a detailed discussion on these domains and ranges.